All right, so this meeting is being recorded and will be posted online after the webinar. And as I mentioned, everyone is muted by default. Feel free to unmute and ask questions throughout or email me after the meeting. And the script that we're going to be going over will be available in the SPEDAS distribution after today under the Projects MMS Examples folder and under Webinars. And you can also find all of our previous webinar scripts under there as well. And one useful thing is the SPEDAS change log. So we have all of the recent changes to SPEDAS online under spedas.org/changelog. And there's also a link to the nightly bleeding edge zip. So I suggest using the nightly bleeding edge zip whenever you're using MMS data, because we're pretty much always adding stuff to that. So you just go to spedas.org/changelog. And this is not just MMS, but everything in SPEDAS, including, you can see there's some Parka solar probe changes, some MMS changes, FAST, Themis, and the bleeding edge zip is just right here at the top. Just click download here. All right, so for the agenda today, first we're going to do a short introduction to the load routines for MMS and their keywords. Then we're going to do ephemeris and coordinates examples. And then we're going to show some fields examples. It's FGM, SCM, EDP, EDI, as well as the digital signal processor, the DSP. And I put ASPOC in the fields examples as well. I don't know if it's technically a fields instrument, but I didn't want to have an entirely different section just for ASPOC. And then we're going to do the EPD examples. That's the energetic particle detector. So EIS and FEEPS. EIS is the ion spectrometer and FEEPS is the electron spectrometer. And then we're going to cover the plasma examples. That's FPI and HPCA. So for the introduction to the load routines, to call the load routines, it's just MMS_load_ and then the instrument name. So for the Fluxgate mag data, it's MMS load FGM. For the search coil, it's MMS load SCM. And there's also MMS load FSM, which is the L3 FGM plus SCM data. And last I checked, these data weren't actually public there, but so if you're a team member, you probably have access to this, but if you're not, I think that data aren't quite available yet. There's also the EDP, which is the electric field double probe data, and then ASPOC, that's the active spacecraft potential control data, and EDI, which is the electron drift instrument, and FEEPS, that's the fly's eye energetic particle sensor, that's the electron particle sensor, and the EIS, which is the energetic ion spectrometer, and FPI and HPCA, those are the plasma instruments. And MEC is the ephemeris and coordinates, so that's spacecraft position and velocity data. And then DSP, which is the digital signal processor on board. And we also have the MMS load TQF, which is the tetrahedron quality factor that's released by the SDC at LASP. And we have MMS load burst segments and MMS load fast segments for loading data availability bars. So this will tell you where the burst segments are and the fast segments, or the fast survey segments are. And these are essentially the data rates, which we'll talk about soon. And most of these load routines all accept the standard set of keywords for actually loading the data. And so the most important is probably a T range, which is the time range of interest, the probe, so for specifying the probe number. It also allows you to do an array of spacecraft numbers. So to load multiple spacecraft at once, it's just give it an array of the numbers you'd like to load. And then data rate, which is, depends on the instrument. It's either survey, fast, burst. And to figure out which data rates are available, look in the header of a load routine, because data rates change based on the instrument. So for instance, you can open the load routine. This is the FGM load routine. You can see in the header, we have data rate, and available for FGM are burst, fast, slow, and survey, and the default is survey. That's another thing to notice, that for all these keywords, except for time range, there are reasonable defaults. And I think for most instruments, if you don't specify a probe, for instance, it'll load probe 1. I think FPI loads probe 3. And we usually default to fast survey or survey mode data, depending on which is available. And so if you load burst mode data, you're going to have to specify the data rate. But if you just want fast survey data for the instrument, you don't actually have to specify a data rate. And the data type keyword, it depends on the instrument. Again, just check the header of the loader tin you're interested in. And so FGM data actually doesn't have a data type, but let's see, EDP. If you look at the header of this one, it'll have the available data types, which is DCE, DCVE, and HMFE. And for details on these data types, take a look at the data products guide released by the team. Those are hosted on the MMS website at LASP. And so all the load routines default to loading L2 data. We also have the non-L2 data, which is L1B, L1A, CIDL, and quick look data. But the non-L2 data requires an MMS team username and password. We have a keyword time clip. So what this does is clips the data down to the time range specified by T range. So when you load MMS data, what we do is go out and look for all the data files that have data within the requested time range, and then we dump all the data in those files into memory. And so if you load without setting the time clip keyword, you will probably get more data than you requested. That is data for times outside of your time range as well. For instance, if you request 6 hours of FGM data, fast survey FGM data, without using the time clip keyword, you'll probably get an entire day's worth of data, because the fast survey data comes in daily CDF files. The reason we do this is because it can take a lot of time to actually time clip the data. And so there are usually better ways of zooming into the time range rather than actually time clipping every time. And by default, we load the data from the LASP SDC. That's the Science Data Center. Also available, you could also change this to SPDF, especially if you're on the East Coast, and load the data from NASA at Goddard by just setting the SPDF keyword. And one thing to note about this is only the L2 data is available at SPDF. So if you want team only data, you have to go through the LASP SDC. And another useful keyword is tplot names. This will return the names of the tplot variables loaded. So for example, you just set tplot names equals to t names. And once the load routine is finished loading the data, t names will be a list or an array of all of the tplot variables that were loaded. Another useful keyword is available. So this returns a list of the files available at the SDC for the requested parameters. So this won't actually load the data. It'll just print the data files, the names of the data files and the sizes of their files, and then a total size of the download. So if you set available, it won't load the data. It'll just tell you which data is available. And that's useful for if you want to load a lot of data at once and you're not sure how long it's going to take or how much hard drive space it's going to take. This will tell you exactly how much it's going to load. And we also have a TT2000 keyword for preserving the TT2000 timestamps. This is if you need the timestamps in nanosecond resolution. By default, we convert to Unix times when we load the data, and you can have there's almost certainly a precision loss when converting from the 64-bit long integers stored in the CDFs to Unix times, which are doubles. So if you want the actual TT2000 timestamps in the CDF files, you have to set this keyword. And the warning here is that most of our routines in SPEDAS can't actually handle TT2000 times. So this is mostly useful for just getting access to those times. the actual times in IDL. And to see a full list of the keywords supported for an instrument, check the header of the load routine you're interested in and just type head or .edit MMS load and then the load routine. So for example, we have FGM open already. There are a lot more keywords that we didn't discuss in there. Things like no color setup. This is useful if you're running on a machine that doesn't have a window or an X Windows or a window manager, like you're running on a server and a terminal. That won't set up any graphics or anything. And there's a no update keyword, which will preserve the original data. This will only load the data from your local hard drive. If it exists, it won't go out to the SDC or SPDF to download the data. We have suffix, which appends a suffix to the end of a tplot variable name as they're loaded. Bar format allows you to limit the variables that are actually loaded into memory. We have a bunch of keywords for controlling the CDF files or the CDF versions, like only getting the minor version, major version, latest version, specifying a specific version to load. You can also return a list of the names of the CDF files. And then some instruments have specific or have special keywords, like FGM has a get FGM ephemeris keyword and keep flagged. So for keep flagged, by default, when you load FGM data, we remove data that are flagged by the team as being non-science quality. And those are just set to nans by default. And you can use the keep flagged keyword to actually turn this off. And there's also ephemeris data in the FGM files that we don't load by default. And you can set the get FGM ephemeris keyword to turn that on. So another thing to note is that when you call, the first time you call one of these load routines, it's going to prompt you for a password or a username and password. If you don't have a username and password, just leave those blank and click save the username and password, and it'll save the blank username and password locally, and it shouldn't prompt you anymore. And a blank username and password will log you in as a public user. And oh yeah, another thing to note is that if you accidentally set the wrong username and password, you can always use always prompt, set the always prompt keyword in a load routine, and this will force it to prompt for the username and password. So I guess we can go ahead and get started with the ephemeris and coordinates examples. So in this example, we're going to load some mech data. Let's compile and then run. So to load mech data for all 4 spacecraft, it's just MMS_load mech, and we set the probe to 1, 2, 3, and 4. If I didn't specify the probe, it just would have loaded MMS1. And in this, we're loading 12 hours of data, and we're time clipping it to those 12 hours. And I explicitly set the data rate as survey mode, but if you don't specify the data rate as survey mode, it's going to load survey mode anyways. And you can see now it's time clipping the data. And if I didn't do time clip here, it would load the entire day's worth of data because these data files are daily CDFs.
So Eric, can I ask a question?
Yes.
So one can get the ephemeris data also by loading the magnetic field data. Is that correct? I'm just asking because this takes a long time because it loads so many parameters. But if somebody is interested in just getting the position, the location, is it faster to load a different way?
So you have to be very careful about loading the ephemeris data in the FGM files because those were added specifically to the FGM files for doing kilometer calculations, 1 CDF at a time. And so if you load multiple CDF files at once, it actually becomes a non-monotonic, it loads the data in a non-monotonic, it has duplicate timestamps essentially for those position variables.
I see. Mm-hmm.
That's actually why
Okay, thank you.
that's actually why we don't load them by default.
Mm-hmm. Okay, thank you.
Yep. But one way to speed this up, since it's loading a lot of variables that you don't need, the best way is probably to specify the var format keyword. This is because this will actually allow you to specify exactly which variables to load. And I'll do another example that should be significantly faster with var format once this is time clipped. So you can do we'll just do one var format. It accepts Unix style wildcards, so stars are match multiple characters and question marks match a single character. So this call right here would load the mech data, only the R variables. All right, for probe 1. So it's, you can see it's now it's only loading the variables with R in the name, and that should be significantly faster. So we called tplot to create a plot of the data. So we created, so we plotted the MMS1 mech data, the R position and SM coordinates, and the velocity and SM coordinates. And here's the plot. The position's on top and the velocity's on the bottom. And so let's keep our script going. So to list all the variables loaded, you just call tplot_names. And that'll print all the variables that are loaded. You can also specify a string to limit the variables, just like with var format. It accepts wildcards, stars for matching multiple characters, and question marks for a single character. So this will only print the variables that have R in them, or R_R_. And so you can see it has ECI coordinates, GSM coordinates, GEO, SM, GSC. And if you want these stored in a variable, so you can loop through them somehow, you can use T names to return them in a variable. So you just call, so tplot names is a procedure and T names is the function that returns the same thing. So you can see now we have R vars, which should be the same thing that was printed out with this tplot names. And we have a really useful routine for converting to Earth radii. So if you want to convert the position data from kilometers to RE, you just call TKM2RE on the variable. So see, now we went and plotted it, appended once it created a new variable with _RE as a new suffix, and then we just plotted that, and you can see now the position data are in Earth radii instead of kilometers. If you want to see the definition of an Earth radii for this routine, just open it up and look at the top, KMNRE. We have that right here at the top. And so this is useful for doing this quick calculation, but if you have to actually get into the variable to access the data and IDL data structures, you use get_data. So that has several keywords. One is data, which returns the actual data values, delimits, which returns the default metadata, and then limits, which is metadata that's set during your IDL session. Usually most of the metadata are set in the delimits though. And for data, it's it's a structure, an IDL structure with .x tag, which is the times, and y, which is the actual data values. So d.x0 would be the first time, or data.x0 would be the first time. And the first data value would be just d.y and then full vector. So that's the first vector for that time. And plot metadata returned by delimits. So you, to find that, it's just another IDL structure. And you can see it has a CDF, but it also has things that specify whether it's plotted on a log scale, spec, and the labels on the plot. So metadata.label should be the labels that are actually plotted over here on the right-hand side of the plot. And most useful with this metadata, though, is access to the actual CDF or metadata from the CDF. So you can do, you call help metadata.cdf. You see the all the metadata from the CDF file. So you can link to variable attributes from the CDF file. Find out exactly all of the metadata there. And another useful routine that we have is find nearest neighbor. It allows you to find times or data values in an array, the closest. So in this example, we're going to use binary search to find the time closest to 6 UT on this day and print that time. And all this, these are stored in Unix times unless you use the TT2000 tag or keyword. And to work with Unix times, we have the routine time string, which will convert the Unix time into an actual string. Then you can convert and see that's 6 o'clock on the dot. And to convert that back to a Unix time, use time_double. And one thing to note is time string accepts a T format keyword that allows you to specify the format however you want it. So if you just want to specify the specific day, you can do this, or if you only want to do time of day rather than including the day, you can do like this. The FFF are fractional seconds. So to only plot there, or only show the time down to seconds, you can just leave off the .fff. And of course, there's a default here. So if you just call time string without that, it'll print it down to the seconds, and it leaves off the fractional seconds. And you can then use where to find the actual index in data.x. And this will allow you to find a variable at a specific time. And this is this should work because closest time is the exact time returned by find nearest neighbor. And so this is the B field value at 6 o'clock. And so just like get data allows you to actually return the data values from a tplot variable, you can create tplot variables from IDL variables using store_data. So in this example, we're going to just use the same data that we returned using get data and the same delimits to create a new tplot variable called new mecbar. And then we plot it, and you can see I created essentially the same plot but without the colors. That's because the colors are were set in the limits. And I should be able to say was L to create the, yeah, so adding limits actually set the colors as well. So that's pretty much how to access the Ephemeris data. Some useful tools are number one, you could use MMS_orbit_plot to create orbit plots. And this will actually go out and load the Ephemeris data and then create an orbit plot for that data. So see, it loads the data. And by default, it's going to load all 4 spacecraft. And so this is an orbit plot for the first 12 hours of the day, on October 16th, 2015. And we specified the coordinate system as SM. But the coord keyword accepts all of the coordinate systems that are in the MEC data files. So you can do GSM, GSE, or any of the others available. And by default, I think it loads GSE data. So if I didn't specify the coord keyword, it would just load. It would load and plot the GSM or GSE data. I'm going to have to update this routine to use bar format to only load the data requested rather than loading all the data files. This is slower than it needs to be. So you can also, some other keywords, you can set the X range and the Y range. You can also change the orbital plane to plot. By default, it plots XY. You can also plot YZ and XZ. And again, you can specify the probes with the probe keyword or probes. And you can change the title of the plot with the title keyword. And just created the plot. See, now we have all 4 spacecraft included. This is the orbit plot for 12 hours on this day. And again, it's the XY plane by default, but you could change that with the plane keyword. And another useful routine is formation plots. So this is 3D plots of the MMS formation. So they call that, and this is at a specific time. So you just give it, the first argument is just the time closest to when you want the formation plot to be created. So in this example, we're using just 6 o'clock on this day. And formation plot actually has a ton of keywords. So just check the header. You can do projections to project the spacecraft positions onto various planes. Projection does all planes, but you can also do XY projection, XZ and YZ to only project onto a single plane. We have the quality factor keyword that turns on the tetrahedron quality factor. It just essentially loads that TQF and includes it, the value in the plot at the top. You can apply rotation matrices, change the sun direction, change the plot margin, and then we also have keywords for setting, for loading and adding various types of vectors to the figure, and for controlling the looks of those vectors. For instance, B field center adds the average B field vector to the center of the figure. It's the average of all 4 spacecraft. You can also add the vector at spacecraft location, change the color, and you can also do the FPI ion and electron bulk velocity, either the average at the center, or you can do the bulk velocity vector at the spacecraft location. And so here's the formation plot. And now since I requested the B field spacecraft, this means plot the B field at each spacecraft. So it's going out and downloading the B field data or loading the B field data into memory. It should include those on the spacecraft, at the spacecraft. So now we have the B field data plotted on the spacecraft. And the thing to note here is that since obviously the B field data is in nanotesla, the kilometers in nanotesla don't actually make any sense. So you can actually scale these using normalization factors. For the FPI bulk velocity, it's FPI normalization, and for FGM, it's just FGM normalization. So in this next example, we're going to use burst mode data for FGM and FPI. We're going to include the ion bulk velocity of the spacecraft, the electron bulk velocity of the spacecraft, as well as the B field at the spacecraft. And we're going to scale those vectors down. Well, for FPI, we're going to scale the vectors down. And for FGM, we're going to leave it at 1. And there's also a keyword, SC size, which allows you to scale the spacecraft size. That's the size of these, the blobs that represent the spacecraft. The default, I think, should be 1. So if you do less than 1, it's going to be smaller. Larger than 1 will be larger. I think that's true. Oh no, the default is 3. So less than 3 is going to be smaller, and larger than 3 is going to be larger. So in this case, it's about half the size of the current. In this next case, it's going to be the size of these things are going to be about half the size of what they are now. And I think we're also including projections. Yeah, so I had the projection keyword. So in this case, we're going to have projections. And if you include the vectors on the plot, it also does projections of the vectors as well. And if you want more examples, there's a crib sheet for formation plots. I think it's in the advanced folder under examples, but it should have formation plot in the name of the crib sheet. And I've really got to update this as well so that it uses var format and takes less time to load the data. Oh, another useful thing is that you can actually, instead of the B field or if you have vectors other than B field or the DIS or the DES velocity, you can specify arbitrary vectors with the vector X and vector Y and vector Z. And there's an example, at least one example in the crib sheet showing how to do this. You essentially just give it the beginning and end of the vectors as a list, and it'll allow you to plot as many vectors as you want arbitrarily. And you can change the colors of the vectors for the user specified vectors, it's just vector colors. And for the B field, it's B field color. And for DIS, it's DIS color, and DES color for DES. So I think that's a different plot. So it's still loading the data. See, now it's loading the burst mode FGM data for this time. And so now we have the vectors at the spacecraft as well as the projection of the vectors onto the various planes. And so that includes both the DIS bulk velocity, the DES bulk velocity, and the B field. And all of this is in GSE coordinates because I didn't set the coordinate keyword.
Hi.
Yeah.
I don't see labels for the bulk velocity and the magnetic field in the plots. How do you do that?
So yeah, we're gonna have to add labels. They're not there yet, but for now, you'll have to check the colors. The DIS color is green. The DES color is blue. So the blue are the electron velocity. The green are the ion velocity, and the red are the B field.
Okay, thank you.
But I'll definitely have to update that and add those labels soon. So moving on to the fields examples. So for just like the ephemeris and coordinates, it's just MMS load FGM to load the data. And in this example, I'm using the get FGM ephemeris keyword because I want to do some kilometer calculations. And I'm loading less than a day's worth of data. So we should only be loading a single CDF file per spacecraft. So it should be, so this get FGM ephemeris should be safe. But again, if you load multiple days worth of FGM data and you load if you use get FGM ephemeris, those data values for the FGMR values are going to be non-monotonic because they include extra values at the boundaries of the CDF file, specifically for doing curlometer calculations with a single CDF file. So you should be able to provide, you could, if you're doing curlometer calculations, you could also just leave this off and use your MEC files or your MEC variables instead. The important thing is that when you use the curlometer calculations, that you do it in GSE coordinates. So the fields and the position values have to be in GSE coordinates. And this is taking a while because we're also time clipping down to the exact 12 hours. The FGM files are daily files, so if I didn't specify the time clip keyword, this would load the FGM data for the entire day. But since we're time clipping, it's going to time clip it down to those first 12 hours. And so another thing to note is that, so when you call tplot, we accept Unix style wildcards, just like with the tplot or underscore names and the t names. So if you can plot multiple variables by using stars or question marks. Again, stars are matching multiple characters and question marks match a single character. So in this case, when we call tplot on this, it should plot the B field vector for all 4 spacecraft, since we have a question mark where the spacecraft number is. And so that you can see that plotted the B field for all 4 spacecraft, 1, 2, 3, and 4 from the top down. And another thing to note is that you'll notice that we have underscore bvec bars, and that's what I'm using for the vectors. If you look, the variable names without the bvec actually have the magnitude attached to them as well. You see, this actually has 4 components because the magnitude is the last one. But a lot of our routines expect vectors to actually be vectors and not have that magnitude attached. So we split the variables by default into a bvec and a btotal. And so for calculating the curlometer or applying the curlometer technique, specify the fields variables, so that's the B field variables in GSE coordinates for all 4 spacecraft, and the position variables for all 4 spacecraft in GSE coordinates. And then you just call MMS curl, set the time range that you want to do the curlometer calculations for. In this case, we're doing 6 hours from 6 to 12 UT, and give it the fields variables using the fields keyword and position variables with the positions keyword. And it just goes out and does all the calculations. And the thing to note is that MMS curl is actually provided by Jonathan Eastwood and Ty Fan. You see, it did the calculations, and then we plotted the total current calculated using the curlometer technique. And of course, created it as a vector. So it's JX, JY, and JZ. And this is for 6 hours. So a useful routine with working with vectors is to use the split vec. So this will split the vector variable into multiple variables. That's the various components. So if you call split vec, it creates jtotal underscore x, jtotal underscore y, and jtotal underscore z. And then we went ahead and plotted the jtotal on top. Close this window out. So I plotted the J total on top and plotted the JX and then JY and JZ. So this is useful for plotting, essentially breaking the vector variables out into multiple components. And this works for any kind of vectors. You can do it with the B field vectors, the spacecraft position and velocity vectors. And the opposite of that is join vec. It allows you to combine multiple vectors or the multiple components into a single vector variable, just calling join vec. You give it the array of vectors that you want, or the array of components as the first argument, and the name of the variable you want to create as the second. And so in this example, it created jtotal underscore new with jtotal x, y, and z, and then we created the plot. And it should be pretty much the exact same thing as the original jtotal. So we also have the search coil mag data, which is MMS load SCM. So we can go ahead and load that data. And by default, it loads survey mode. You can also specify burst. Let's check the header for the various data rates. So we have burst, fast, slow, and survey. And for data type, there are several options. I usually just use the default for those. And you can see we plotted the SCM data. So this is the Vx, Vy, and Vz from the search coil mag. And again, since we didn't specify the probe here, we didn't load multiple probes, we just loaded probe 1, because that's the default probe that's loaded when you call MMS load SCM. And we have a useful routine called TD power spec, which calculates the dynamic power spectra. And so we're going to calculate dynamic power spectra of this SCM time series. And one thing to note is that the defaults for these keywords should be changed based on the data rate. And so if you're wondering what options to use or what options the team suggests to use, look at the crib sheet for SCM. We actually have burst mode examples as well as survey mode examples. And I just copied and pasted from the crib sheet. So we did the dynamic power spectra, and you can see it created X, Y, and Z variables. And we're going to go ahead and call tplot. And one thing to note is that we had a question mark here for the X, Y, and Z. So this should plot X, Y, and Z. And then I used the add keyword to add these. And so the add keyword to tplot actually adds the plot to the current tplot window, and it adds it to the top. So right now we have just the SCM data as a vector. When we call this, it should add all 3 components of the dynamic power spectra to the top. So we have the X, Y, and Z, and then the SCM data that we previously plotted is down at the bottom. So without the add keyword, it just would have plotted the dynamic power spectra without this at the bottom. So for electric field data, it's just MMS load EDP. By default, it loads the DC electric field. There are other data types available in the EDP files, such as the spacecraft potential. And the thing to note here is that data type usually accepts an array of, so you can load multiple data types at once. So in this case, we're just going to specify probe equals 4. We'll load 12 hours of the electric field and the spacecraft potential, and we're going to time clip it down. All the data types and the data rates available in this load routine, just check again the header data type as the data types, and this is missing spacecraft potential. And the data rates are burst, fast, slow, and survey. And some data types each data type has specific data rates. So if you're looking for a data type and if we're at a specific data rate and it's not there, try one of the other data rates. All right, so in this case, we plotted the DC electric field and the spacecraft potential. So you have the electric field on top and the spacecraft potential on the bottom. And another data product is the E-field spectral density. And again, in this case, you have to specify the data rate of survey because I think the spacecraft potential and the DC electric field are technically data rate equals fast. You can see it in the variable names as well as in the file names. But for the HF-ESP data, those are in the survey files. So we're gonna go ahead and load that data. And create the plot. And another thing to note is that if you're unfamiliar with the variable, you can check the variable attributes in the CDF metadata. I showed that earlier. It's worth mentioning again, because I usually, this is where I go to find out about variables. And these are the delimits .cdf.vat is the variable attributes directly from the CDF file. So you can see the label axis, variable name, actual description of what it is. And so another load routine is DSP, that's the digital signal processor on board. And so to load the EPSD and the BPSD, that's the electric power spectral density and the magnetic power spectral density, you just set data type equals EPSD and BPSD. And I think DSP has a lot of different data types, I believe. Okay, so it loaded the data, but we should check the header and see. Yeah, so we have EPSD, BPSD, and SWD. I'm not sure what SWD was. But we can plot the EPSD and the BPSD. And the EPSD is on top and BPSD is on the bottom. And again, I'm using wildcards, stars for matching multiple characters, and question marks for matching a single character to just create the plot. And the single character is the E and the B, and the multiple characters are spacecraft name, DSP, and then the suffix. And of course, there's also the omni. It also has the individual directions, the non-omnidirectional loaded as well, which we didn't create a plot of. In addition to all of that, you also have the EDI, that's the electron drift instrument. So it's just MMS load EDI. In this case, we're loading a full day's worth of data. And we're plotting the E field from that instrument as well as the drift velocity from that instrument. You can see, and we're doing it in GSM coordinates, so you can see it has the labels GSM, Vxvy for the VC for the drift velocity, and EXEY, EC for the electric field. And finally, we also have ASPOC, which is just MMS load ASPOC. This is the spacecraft potential control. And we're going to load the entire day's worth of data. And this allows you to tell when the ASPOC instrument was on. You can tell it came on in the afternoon. So moving on to the EPD examples, it's EIS and FEEPS. We'll start with the electron data by loading MMS load FEEPS. And we're going to load 12 hours of data and time clip it to 12 hours. And then we're going to plot the omnidirectional intensity, electron intensity, and the spin average omnidirectional electron intensity. And for keywords, just again, open MMS load at FEEPS. And so data type is based on, depends on the level. So for L2 and L1B data, it's electron and ion. For L1A, they're different. And data rates are burst and survey mode. And of course, the default is survey mode. But we also have a keyword for data units. for specifying only certain data, certain units for calculating the spin average and the omnidirectional calculations. I think by default we do count rate and intensity. So we calculate the omnidirectional and the spin average for count rate and intensity, automatically onloading the data. So a few other things to note is that we have a lot of extra post-processing once we actually do the loading for FEEPS data. So that includes correcting the energy tables, applying flat fill corrections to the ions, removing bad eyes and energy tables or energy channels, only using the active eyes. And then so in the CDF files, these variables actually have an integral channel attached to all of the variables, and we split that out into its own variable. And we also remove sunlight contamination, and then we finally calculate the omnidirectional spectra, and then spin average those spectra. And if you specify the num smooth keyword, it'll create a smooth variable, and I think that's in seconds. So yeah, so specifying num smooth equals 19 will smooth over the full spin, which should be essentially the same as spin averaging. But it gives you more control over the actual averaging, and that you can specify that and smooth over a few data points or more data points, depending on what you're doing. And just like before, the default probe here is probe 1. If you don't specify a probe, it's just going to load probe 1. And if you don't specify a data rate, it's going to load survey mode. And if you don't specify a data or a data type, it'll load electron data, since FEEPS is technically an electron instrument. And while that's doing the calculations, it's worth also pointing out that we have several crib sheets for working with these, where you can find more examples, like MMS load EAS crib for the EAS, and then it's MMS load EAS burst crib for the burst mode EAS data, MMS EAS angle crib for creating angle plots with EAS data. And for FEEPS, we have MMS load FEEPS, and then MMS FEEPS spec. This actually creates spectrograms based on sectors rather than energy. I think this is mostly useful for determining the effectiveness of sunlight contamination removal. So while those calculations, we can go ahead and talk about doing get data on an energy or an energy spectra or spectra values in general. Calling get data and returning the data with D. When you call help, it'll have, as before, it'll have the X values, which are the Unix times, the Y values, which are actually the Y, which are actually the data values, and then you have D.B, which is the energy table. Those are the Y values on the spectral plot. So, which should be created very soon. I think we're time clipping right now. And one thing to note about printing the D.B values, you print the energies. Some of these, for some instruments and data rates, vary with time, like FPI burst mode energy spectra. If you were to do D.B, it would print a lot of data values because each the energy table changes with each time step. So that would, in general, you don't want to print the entire data values or the entire variable if it's varying with time, because might crash your IDL, but it'll at least fill the console with the data values for each time. And you can see now it's using the removed the bad eyes using the table from 2017. This always seems to take a lot longer when other people are watching. Another keyword available for FEEPS is ignore telescopes. You can actually tell it which telescopes to ignore when calculating omnidirectional spectrograms. And should be pretty close to being done. And these 500 keV variables are those are the integral channels that are being split out from the individual T-plot variables. And clean sun removed is the data that's been had the sun removed, and you can go ahead and look at the load routine to see exactly what's happening in there. So we've split the integral channels, removed the sunlight contamination, and already done the spin average or the omnidirectional calculations and the spin average. And so now we've plotted the omnidirectional non-spin averaged on top and the spin averaged on the bottom. And so I guess continuing on. So I mentioned that help, or that get data returns the data for the variable, and running help on it will give you the show X, which are the time values, Y are the data values, and at each time, and V are the energy table. So in this case, since it's not time varying, I just printed it out, and these are the energy values, or the energy table for this specific time. And again, it's just D.V. With variables that are multidimensional, so like distribution function data that varies with angle and energy, then instead of D.V, it's D.V1 and D.V2. Or if you have a variable that depends on phi, theta, and energy, it'll be V.1, V.2, and V.3. But in this case, we're just working with energy spectra, so it's just D.V. And sometimes you want to actually, for energy spectra, you want to flatten or create a single plot for a single time of the energy spectra. So in that case, you just call it flattened spectra. That's essentially intensity versus energy in this case. And what that does is it allows you to select a time on the plot that you want to create the energy spectra for. So I guess we can just select around 2 UT. And that created intensity versus energy plot for both of the spectra in this plot at almost 2 UT. And if you forgot a keyword, like if you want to set Y log Y log or X log, you can, but you want to plot at the exact same time without having to re-click on the time, you can just use replot. So in this case, we're calling it with xlog, ylog, PNG to create a PNG file and giving it the file name of Spectra, which would be spectra.png. And so instead of requesting a time, it'll just use the previous plotted time. And then in this case, we have the y log, or the y-axis is on log scale, as well as the x-axis. And there's also keywords for controlling the legend names. And again, to check all the power that it has, just look at the header. It should have all of the keywords. You can turn off the legend. You can change the colors. Also useful is you can do conversions. By default, it just uses the units for each plot, but you can also convert it to KeV. Say if you have data from one instrument that's in KeV and data from another instrument with a y-axis and EV, using to KeV, we'll use the metadata internally and convert both to KeV. And same thing with to Flux. By default, it just uses the intensity units from the variable. And so you would want to, if you're using multiple, if you're plotting spectra from multiple instruments, you'll want to convert it to a common units, or a common set of units. Another keyword is bar, which actually adds time and bar. Bar will add a vertical line at the selected time on your T-plot window, and time allows you to specify a time via keyword rather than actually selecting it on the plot. So in this case, we're going to create the Spectra at 6 o'clock, and it should have created a bar. Yeah, so there's a vertical bar here right at 6 o'clock. Ooh, another useful routine is MMS FEEPS pad. This is the electron pitch angle distribution for FEEPS. You just call it with MMS FEEPS pad. And without any options, it'll of course default to probe 1 survey mode data. But if you, and the full energy range, you check the header, there's a bunch of keywords to control all of that, including the bin size, the energy range, the probe. But by default, it just loads the full energy range, or creates the pitch angle distribution for the full energy range electrons for probe 1. And in this case, we plotted it. It also creates a spin average copy of that. So the T-plot window should have the non-spin average pitch angle distribution on top and the spin average pitch angle distribution on the bottom. And so I mentioned the energy ranges can be limited using the energy keyword. So you just set energy, and it's in KeV. So setting the energy to 1 to 200 is 1 to 200 KeV, and 200 to 300 is 200 to 300 KeV. So we're actually creating 3 different, or technically 6 different spectra here, or pitch angle distributions here. One non-spin averaged and 1 spin averaged for this energy range, and 1 for this energy range, and 1 for this energy range. And then we're going to plot the non-spin average for these energy ranges. And you can see just calling people out names. The last variables created with a pitch angle distribution. It also created a smooth version and the spin average. We're going to plot the non-spin average. So you can see in the labels, it's 1 to 200 KeV on top, and then in the middle, it's 200 to 300 KeV pitch angle distribution, and then the bottom one is 300 to 400 KeV. And another thing to note is that flattened spectra works on any type of spectra, spectrograms, including pitch angle distributions. You can also plot a line plot, have line plots on the same window, and it'll just ignore those line plots and only create the spectra for the actual spectrograms. In this case, we're gonna create spectrogram. Let's try it at 2. Of the pitch angle distribution at 2. And you see we have the black is the 1 to 200, the blue is 200 to 300, and the green is 300 to 400. And on the y-axis, it's the intensity, and on the x-axis, it's the pitch angle. So it's 0 to 180, the actual values. And another thing to note is that it will warn you if it's finding variables with units or different units. I'm not sure why it's doing that in this. Oh, yeah, I'm not sure why it's doing that in this case. It should be fine in this case. So for EIS data, it's just MMS load EIS. And the data types are EXTOF, that's the energy by time of flight data, and the PHXTOF, that's the pulse height by time of flight data. So in this case, we're going to load both, but just specifying data type and giving it an array of both. And just like with FEEPS, it calculates the omnidirectional spectrograms and also spin averages the omnidirectional spectrograms. And we're going to plot the spin average energy by time of flight and pulse height by time of flight once they're done calculating. And just as before, notice we didn't specify probe, so we're loading probe 1 and survey mode data, since we didn't specify a data rate either. And should also open this and look at the header. So just like with the FEEPS, we have a data units keyword, and the options are flux, CPS, and counts. CPS is counts per second, and by default it just uses flux. And if you didn't specify a data type, it would load energy by time of flight data. And created a plot. So we have the energy by time of flight data at the top and the pulse height by time of flight data on the bottom. And just like with FEEPS, we also have MMS EIS pad, which allows you to create the pitch angle distribution for EIS. So in this case, we're only going to do energy by time of flight, just to speed things up. And you can open this and look at the header for the options. Just as before, there's an energy keyword for specifying the energy range. Species keyword, in this case, we have a species keyword for specifying which species. And there's a size PA bin, which specifies the pitch angle bins. Data units, again, for specifying the units. Scopes allows you to specify only specific telescopes to include. And there's also combined proton data, which combines the energy by time of flight and pulse height by time of flight data to create a combined spectrogram. And that's experimental. So I would definitely contact the team or the EIS team before publishing data that use these combined data products. All right, so we were able to calculate the pitch angle distribution. And so you can see it created the pitch angle distributions at specific energies, and then it also created over the full energy range. And that's one of the differences between FEEPS and EIS. That they actually calculate the pitch angle distributions at specific energies as well as over the full range. So go ahead and plot it for the full range. So we have the non-spin average on top and the spin average on the bottom. So moving on to the plasma examples, that's FPI and HPCA. And there are all kinds of crib sheets with FPI and HPCA data in both the basic folders and the advanced folders. But to note, we have FPI crib, FPI burst mode crib, HPCA crib, HPCA burst, and then FPI angle. I think there's an HPCA angle now. And then there's the get spec, MMS part get spec, which allows you to convert or take the distribution function and create or calculate the energy spectrograms, gyrophase spectrograms, pitch angle distributions, as well as moments directly from the distribution function. And that allows you to do it with FPI and HPCA. There's also an advanced crib for that with more advanced examples. We also have slices to the distribution functions. And there's a crib sheet specifically for FPI slices, and another crib sheet specifically for HPCA slices. And we have routines for visualizing the distribution functions for FPI and HPCA in 3 dimensions. And we also have routines that allow you to create or combine spectrograms or any arbitrary T-plot windows with the 2D slices called MMS splitbook or MMS splitbookify, and the crib sheet is here. And I'll show examples of that. So let's go ahead and load some FPI data. So one thing to note is that if you look at call MMS load FPI without probe specified, I think it loads probe 3 instead of probe 1 by default. But in this case, we're loading probe 4. And we're setting the data type to DES moms and DIS moms. That's the moments for the electrons and the ions. And we're loading burst mode data, and we're going to try to load 10 minutes of burst mode data. But in this case, since we're not going to be time clipping, it's probably going to load more than what we're requesting. And again, check the header for the available options. So for instance, data type for L2 data, the options are DES dist and DIS dist. That's the actual distribution function data for electrons and ions, or DIS moms and DES moms for the moments data. And the available data rates for FPI are fast and burst, at least for the L2 data. And another important keyword is center measurement. And both FPI and HPCA have this keyword. And you probably want to use this keyword because, so one difference between FPI and HPCA data with all the other instruments is that these data values are actually at the beginning of the accumulation interval. And the other instruments like FGM data, DIS data, FEEPS, all the other instruments other than FPI and HPCA have the data at the center of the accumulation interval. So when you load these, you really want to be using center measurement, especially if you're plotting them and comparing them with data from other instruments like FGM. So you can see we created the plot, and notice that this time along the x-axis, the times don't actually, so we tried to load 1300 to 1310, but we actually got data from, I think around probably 1256 through 1310. And that's because we found some data that was earlier data and loaded that in as well. But if you set time clip, it would actually time clip it to 1300. And notice that that there are gaps between the files here. And by default, interpolates through the gaps. The T-plot window interpolates through the gaps. So you can remove the gaps by calling TD gap, and then giving the variables that you want to remove the gaps for. In this case, we're going to remove the gaps for the DES energy spectra and the DIS energy spectra. And then I gave it the overwrite keyword, because if you don't give it the overwrite keyword, it creates an entirely new variable. But if you give it the overwrite keyword, it just overwrites the current variable. So this should remove the gaps once we.
So Eric, can I ask a question?
Yeah.
About the center measurement for FPI. When you do that, you do it data point by data point, looking at data point by data point, or do it for the whole interval? I guess the whole interval has the same resolution, so you apply it to the whole burst.
Yeah, we do it.
Right?
Yeah, we do it to the entire time series.
Okay. Okay.
And it's based on the metadata in the CDF file. They actually have the beginning and the end, and we just calculate.
Right, and they're all the same, meaning like, each for the whole interval it's going to be the same time resolution. You wouldn't have any problem.
Yes. Yep. So with the TD gap, you can see it just overwrote the variables, and now we can call tplot. And one thing to notice, if you call tplot with no options, it just recreates the current plot with the current variables. So if you modify a variable that's currently plotted, you can just call tplot and it'll recreate the plot. So in this we have the electron spectra on top, the ion spectra below that, and then electron bulk velocity, ion bulk velocity, and then the electron density and ion density. And you can notice that for the we removed the gaps for the energy spectra, but I didn't call it on the line plots, so it's still interpolating to those. You can call TD gap on the line plots or the line variables as well, and then remove those gaps, just like you can with the energy spectra. And so HPCA is very similar. It's just MMS load HPCA. And just like FPI, we really should be using the center measurement keyword here. And the data type is different though. For HPCA moments, it's just data type equals moments. And I think by default, it loads moments data, so you really don't have to specify data type if you're just going after the moments data. So we loaded the moments. And so we plotted H plus density on top, and H plus temperature, and H plus velocity. But if you list the variables, it loaded the data for all the species. So we should have H plus, HE plus, HE plus plus, and O plus there as well. And again, it should have, we didn't use time clips, so it loaded data outside of the requested time range. And it's worth also pointing out that I mentioned earlier that there are faster ways to zoom into the data than time clipping. The best way is to use t-limit. And that allows you to select the time range that you want to zoom into. So we can select 1300 to all the way through 1310. And you see it actually zoomed into the plot very quickly. That's because with time clip, you're actually time clipping every variable that's in the CDF file, and it's usually a lot more variables than you actually want to be time clipping. So I always prefer to use t-limit to zoom in. And t-limit has a lot of options. It can specify the time instead of if you do an empty call with no options, it'll use the cursor. But if you give it times, it'll just allow you to actually specify the times as an argument. You can also reset the limits with limit full. Go back to the full time range as before. And you can also use t-limit last, which will go to the last one, the previous one. So we just went right back to what we selected before. So if you want to load HPCA flux data instead of the moments, so this is creating energy spectra, you just specify data type equals ion instead of data type equals moments. And again, we really should be using the center measurement keyword here. And I don't think I opened the HPCA load routine, but so look at the header. You see data type. So for L2, it's ion and moments, and that's the flux data and the moments data. And CITL and L1B have different data types available in those files. And the data rates available for HPCA are burst and survey. And of course, it defaults to survey. Right, and so we loaded the HPCA flux. So the variables loaded. And so one thing to note about the HPCA flux data is that it is actually stored as with the full angle information in the variables. So for instance, if you call get data on the phase-space density variable, you can see it's a function of V1 and V2, so it's angle and energy. And since the HPCA data is multidimensional, you have to actually sum the data over the full field of view and average over a spin to calculate the omnidirectional energy spectra. So it's essentially just calling these two routines right here, MMS HPCA calc A nodes, and specifying the field of view that you want to sum over, and then MMS HPCA spin sum. So if you don't specify the AVG keyword, the average keyword, it'll sum over the spin, and if you do specify it, it'll average over the spin. So, and for a full omnidirectional spectrogram, you have to either spin or average over the full spin for HPCA. And so this creates new variables that have the elevation, which is the field of view, 0 to 360, and then spin averaged. The spin averaged ones are the full omnidirectional spectra. So in this T-plot call, we're going to plot the H plus, the O plus, and the HE plus, and the HE plus plus. And that would be the full omnidirectional spectrograms. And another thing to note is the calc A nodes. Also, if you only want to look at specific A nodes, there's another keyword called A nodes that you can specify other than field of view. Of course, you can set field of view to 0 to 180 to only do half the field of view, or you can specify specific A nodes using A nodes. And it also accepts the probe keyword and suffix to append another suffix to them. It should be almost done. I think the way calc A nodes works is that you don't actually have to specify a probe, but with HPCA spin sum, you do have to specify a probe. And you can also change the data type for spin sum, but the A nodes calculation, I think this works with all data types. And I always use the AVG keyword because that's what recreates the average over the spin averaging instead of spin summing recreates the energy spectra that can be generated directly from the distribution function using MMS Parka get spec, which we'll show in a minute. All right, so we created the full omnidirectional spectra, variables with people and names, with thousands of variables here. All right, so we can, if we use call get data on here, see now that it's just X, Y, and then the V for the energies. So you can print the actual energy values, and you can put the Y values at the first time for these energies. And in this case, we're also going to just go ahead and create a plot. So this is the omnidirectional energy spectrograms for H plus on top, O plus below that, HE plus, and then HE plus plus. And so another routine that's really useful is called T-plot multi-axis. This allows you to add another spectrogram or a line plot over a spectrogram. Probably best to just create an example here. So on this plot we have the electron spectrogram or electron spectra, the ion bulk velocity, and the ion spectra, energy spectra on the same plot. And then on the right-hand side, we have we're overplotting the electron number density over the ion spectra. And you can see that the electrons number density are plotted over that spectra. And to see how this works, just open the header. You essentially give it the names for the windows in the first argument, or the left, that you want to use the left on as the first argument, and the right names on the second argument, and then the position of the right names as indexes on the as the third argument. And what happens is the color table and the chosen the color table here is pushed to the right, and then we add the label for the line plot on the right hand side. I think one thing this is really useful. I didn't use. I probably should have chosen a different example, but a better example would be like the electrons and the spacecraft potential plotted over the electrons, because then that shows the spacecraft potential contamination in some cases. And I mentioned before that MMS part get spec will allow you to generate the distribution function, or generate various things using the distribution function. For instance, the energy spectrograms, the pitch angle spectrograms, as well as calculate the moments. And the idea is it goes out and loads all of the support data, and then calculates, does all the calculations directly from the distribution function. So let's go ahead and do it. And the MMS part get spec accepts the instrument keyword, and by default it loads FPI data. I went ahead and specified it explicitly to make it clear that there's an instrument keyword, and you can change it to HBCA. There's also a species keyword to change the species, and in this case we're doing ions, and setting the data rate to burst and trying to generate the pitch angle distribution, energy spectra, and moments for 1 minute of data as specified in the T range. And I specified the probe 4 here. And another thing to note is that the header of this should have all the documentation, or a lot of the documentation specifically for MMS part get spec, and more documentation can be found in the underlying routine. So MMS part get spec is really just a wrapper around a routine called MMS part products that actually does all the heavy lifting and the calculations. And that's where you'll find most of the keywords and documentation. For instance, you can specify, you can change the units to flux, or you can just create the plot the distribution function By default, it's calculating energy flux though. And so again, if you're using this, I highly suggest going and checking out the MMS Park Get Spec crib sheet and the MMS Park Get Spec Advanced crib sheet, which has a lot of examples in there. And once this is done, we're gonna plot the DIS energy spectra that was calculated directly from the distribution functions, along with the DIS energy spectra stored in the moment CDF files. And energy spectra generated in this call would be this one right here. It's on top. And those two should match. And if you were to call MMS Park Get Spec with instrument HVCA and species H+, the energy spectra generated should match the spin average energy spectra for HVCA that we calculated up here. And I left that example off because it's probably take too long. Oh, another thing to point out is I'm only using the, currently only showing the pitch angle distribution, moments, and energy spectra, but there are other options like phi, which is the azimuthal spectrogram, theta, which is the latitudinal spectrogram, gyro, which is the gyro phase spectrogram, multipad, which calculates a pitch angle spectrogram at each energy. And there's another routine for combining these MMS Park Get pad. And this is useful if you want to limit the energy range for the pitch angle distributions. You can actually call MMS Park Get pad, and it's much faster to use multipad to generate various spectrograms over energy ranges. And you won't have to do these calls over and over and over again. And so there are input keywords that allow you to limit the energy range, limit the phi range, limit the theta range, limit the pitch angle range, and the gyro phase range. So these are pretty flexible. I definitely suggest reading the header and checking out the crib sheets for these as well. So if you can generate the moments, for instance, by and limit the energy range or the pitch angle range, generating the moments. But if you do that, I suggest generating the moments first without any special options, and then comparing those to the moments in the CDF file to make sure that without the special options, the values match those that are released by the team. And if they don't, try to understand why those don't match. But they do in most cases. I think also that if you don't specify a probe in this case, it actually does all probes. So that's another thing to look out for.
So Eric, a question here about, you just mentioned that you can use this to calculate moments, like let's say FPI, for example. And I know the FPI team, to get moment, they have to do a lot of corrections, like to the photoelectrons and all that. Say, let's say for electron moment. Does this routine do that, or it doesn't do that?
Yes, it does.
It does.
And,
Okay.
yeah, and it uses, yeah. And we use Dan Gerson's photoelectron model.
Okay, great, wonderful. Thanks.
Yep. This took a lot less time to calculate than when I ran it yesterday. Wonder why that is. So I guess while all of that's still being calculated, I can go ahead and talk about 2D slices. So we can also create 2D slices of the distribution functions using MMS part slice 2D. If you're familiar with SPEDAS 2D slices, this is just a wrapper around the SPD underscore slice 2D routine. It's specific for MMS. And this will actually call MMS or call SPD slice 2. Well, first it'll load the support data required, and then it'll call SPD slice 2D to calculate the slices, and then it creates the plot with SPD slice 2D plot. So the idea is to have a single call that creates the plot with the 2D slices. And I didn't specify it here, but there's a rotation keyword. There's a bunch of keywords. And it allows you to specify the energy range, change the interpolation options. By default, in the latest bleeding edge, we're using geometric interpolation. And the actual description of the interpolation options are in the header right here. So, and 2D and geometric interpolation takes longer, but it gives a more realistic view of the distribution. And this probably has more options than any other routine that we have. So you definitely want to review these and take a look at the crib sheets for these. And so in this example, we're going to specify a time. So we're going to do it at 1306 and use burst mode data and species to ions and instrument of FPI. By default, again, it uses FPI data. But I wanted to specify it specifically here just to be clear that there's an instrument keyword and you can change it to HPCA if you want. And
Eric, I have a question. Oh, sorry.
Yeah, go ahead.
A question about the time. When you specify the time, it will find the closest time to that for the. Yes. Okay, good. And can one specify a range and it will produce multiple, or just one time?
So if you specify a range, it'll average.
Oh, I see. Okay. Okay. So if you want to have multiple plots for multiple times, then you do a for loop or something to go through it.
Yes. Yeah.
Okay. Thank you.
Yep. And in addition to, so if you specify a time, you can also give it samples keyword and tell it to specify more samples. You can also specify a window with the window keyword, which is length in seconds over which the time is averaged.
Okay, so the sample keyword is you want to, let's say, average over 5 samples, then you do that. Is that right?
Yes.
Okay.
Yep, samples equals 5.
Mm-hmm. Thanks.
And these energy spectra should be almost done. Should have been done a while ago. All right, so this is a warning. You can also turn the warning off with the silent keyword. And this is MMS Parka spec. It warns you that the values might be different, and to check to make sure that they're not before. The values might be different from the official CDF data, and to check that they're not before publishing. And if they are, ask questions, either or ask the team. You can also copy me, and I might know, or at least be able to figure it out. And another keyword for 2D slices that's really useful is units. By default, the slices are of the distribution functions, but you can also call unit or set units to do the conversion to a different set of units, like Flux will plot the data, create the slice in energy flux units instead of distribution flux units.
Hello, Eric. I just want to ask you that whether we can specify the coordinate system also.
Sorry, could you repeat that?
Yeah, sure. Like the 2D slices, the energy slices, can I just denote the distribution function? Can you?
The coordinates?
Okay. Yeah. Coordinate system. Yeah, means that let's talk about the field aligned coordinate system maybe.
Yeah, so that's the rotation keyword. Let's see,
okay.
Where's the rotation keyword? So it's the rotation, and by default, it uses XY, which is just the x-axis is along the data's x-axis, and y is the data's y-axis. But you could also do VV, which is x-axis is parallel to the V field, and the bulk velocity defines the XY plane, and BE. And so there are actually several options here.
Yeah. Okay. Thank you.
And you can also do a custom rotation to apply a custom rotation matrix. It's just a 3x3 matrix. So there are several options here for changing the coordinate system.
Okay. Thank you very much. Yeah.
It looks like it's finally doing the calculation for the FPI spectra. And this is the pitch angle distribution, the energy spectra, and the moments for FPI ions in burst mode in 1 minute of data. And since it's taking so long to do these calculations, I might skip over the HPCA and the energy flux slices. If these calculations are taking a lot longer than yesterday, those calculations are going to take a lot longer as well. All right, so notice it created several new variables, the underscore energy, underscore PA, average temp, density, efflux, flux, pressure tensor, spacecraft current velocity. So get just T-plot names, show the T-plot names, and we'll go ahead and plot. So the top plot here is, or the top panel shows the energy spectra calculated directly from the distribution function. And the bottom panel is the energy spectra from the moment CDF files. And since in our call to MMS get spec, we limited it to 1 minute of data. There's only 1 minute of that data. So we can use T-limit, zoom in to that minute, and they should be the same, though they're on different color bars. I'm not sure why the color bar disappeared on the bottom one. You have to look into that. Also do flat spec on these. Y log and X log, and so click. It should create the actual spectrogram. Yeah, so the black is the energy spectra calculated directly from the distribution function, and the blue is the energy spectra from the moment CDF files. And since the units were different on the plot here, the unit labels were different. I added both units, but they should be the same. So for the 2D slices, we'll go ahead and the FPI ion burst mode for the time closest to 1306. And while that's actually being calculated, another useful thing, the next useful thing is, what if you want to take one of these T-plot windows and add the 2D slices to the right-hand side? You can do that with MMS Splitbookify. So what you do is create a window, a T-plot window, and it can have pretty much anything plotted in there. In this example, we're going to plot the ion energy spectra, the ion number density, and the parallel and perpendicular temperatures. And then we call MMS Splitbookify, and it creates slices and adds them to the right-hand side of the window. And we should open that. And this has a whole lot of options as well, and they should all be documented up at the top. There's a slices keyword that actually allows you to specify the specific slices to include. I think by default it's XY, XZ, and YZ. But you can also do the field aligned slices. And there's a keyword for saving the files as postscripts. And this actually does generate an array of images, or a list of images, one at each time, and it uses the time steps in the top panel. So you can specify, set the keyword seconds to specify a number of seconds for each slice is produced at, or time step, which is energy specifying the interval at which the slices are produced at. I think seconds is probably most useful. So you say seconds equals 1.5, it creates a plot at every 1.5 seconds. And it draws a vertical dashed line on the figure at where the slices are actually created at. So while we're still creating that 2D slice, I can show the flipbook example. So this is the one that I calculated yesterday. It was FPI ion splitbook, and in fact, I think it's this exact example. And this is with the video keyword, so it saved a video of these slices. And I said seconds equals 3, so it's every 3 seconds. So you can see we have the T-plot window on the right, or the left-hand side, and the slices, that's the Vxvy on top, Vz, Vx in the middle, and then Vx and Vy on the bottom. And see there's a vertical line drawn where the slices are taken. And by default, it should save a bunch of PNG files for each slice. If you don't specify the video keyword, the video won't be produced, so you'll have to specify the video keyword if you want the video. And just like with these other routines, it accepts that instrument keyword for changing to HPCA, and of course data rate for changing the data rate to burst mode instead of, by default, it's probably using fast survey here, even though we have burst mode. And since that's taking forever, I definitely suggest looking at, if you're using Flipbookify, to take a look at the advanced crib sheet MMS Flipbook crib. It has a bunch of examples in there for how to do that. And since we only have, I think, 6 minutes left before that, I think the meeting will probably close at 6 minutes because I only set it up for 2 hours. Oh, here's the slice, finally. So this is the distribution function for FPI ions, burst mode. And you can see the time isn't exactly 1306. It actually gives you the exact time in the title here. It's 1305.59.908 through 1306.058. And the 1 here is how many samples are included. That's just 1 sample. And again, this is Vx versus Vy, but you can change that with the rotation keyword to do field aligned. And if you specify units of efflux, the units here currently are in distribution function units. Change it to efflux, it'll be efflux units, and create an efflux plot instead. And I guess we can go ahead and jump to the angle plot since we have so little time. If you want to create angle plots, it's just MMS FPI ang for FPI, and you give it the time as the first argument. And again, it uses the time closest to your requested time. And so what this does is create, I think, 4 plots. It's angle, so azimuth versus zenith, and then azimuth versus energy, and zenith versus energy, and then pitch angle versus energy. And the azimuth versus zenith angle include pitch angle contours, or contours for the pitch angles. And just like we have one for FPI, we also now have one for HPCA. So it's just MMS HPCA ang. And I think that one's missing the pitch angle energy plots. That one only includes angle, and angle energy plots. And you set the PNG keyword to save the plots as ping files. And just as before, if you check the header, it should have the header and the crib sheet should have all the options documented in several examples. And you can disable the contours, the pitch angle contours on the angle plots with no contours keyword, but they are by default. And there's also a center measurement keyword that you'll want to set. I'm surprised we're not setting that by default, but yes, you'll definitely want to set the center measurement keyword when doing this as well. So since we only have a few minutes left, I'm not sure when this is going to cut out. I am going to be putting this this entire script in the SPEDAS distribution after this at projects, MMS examples, and webinars. And we have all of our previous webinar scripts in there as well, so you can dig through some webinars that we have. I think there's one on various T-plot. We had one on T-plot options. We had one specifically on the EPD instruments at one point, one specifically on the plasma instruments at one point. So if you're interested in digging in beyond all the current crib sheets, I suggest reviewing the webinars, the previous webinar scripts. And I'm also going to post this video online for others to read and look at. And if you have any questions after this, feel free to email me. You can use my direct email, or you can just use my full name at ucla.edu. They both go to the same place.
Thank you very much, Eric. It's been very helpful.
Yeah, thank you. And this is probably not going to finish before the webinar finishes, so I guess we'll just go ahead and end it now. Thanks for calling in, everyone.
Thank you.
I'm always
Where can I access this video again?
sorry, could you repeat that?
Where can I access this video again?
It will be on linked to from spedas.org later today. We're probably going to put it on YouTube.
Okay.
And I think we're also going to upload it to a Dropbox folder for people outside of, or people in China, since YouTube's blocked there. Or not Dropbox, box.com.
Okay.
Oh.
Thank you.
Yep.
Thank you very much, Eric. Yeah.
Yep. Thanks for calling in.
Mhm.